Okay. Any questions regarding properties of negative feedback? Prior to this, we have started with general feedback structure, if you can recall. And after covering general feedback structure and important elements in the general feedback structure, we have moved to the properties of negative feedback. One advantage of this module is all topics are very easy, it's theoretical, and we can score good marks in examination also. Okay. So therefore, I would suggest to make a material out of this. Okay. All right. This materials, as you can see in this Google Classroom. Okay. So this is a year related one. Let me open up. I hope everybody received IA marks. Till end of the day, you have a clarification. You can just, if any variation in marks, you can just update me on that. Okay. And all the blue books that your written test has to be retained with you and submitted once you come back to the college. You cannot lose that, it is important material. Kindly submit it before we finalize IA marks of this semester. Okay. All right, let me review the things what we have covered in the last class. Properties of negative feedback. Okay, so in this we have covered few properties already. I will skip those things. Gain, desensitivity we have covered in the last class, and relevant expressions also we have covered. So as you can see here, we have shown that DAF by AF, which is nothing but fractional change in amplification with feedback, equals fractional change in amplification without feedback, that is dA by A multiplied with 1 by D. As you can see, there is a 1 by D factor here. Okay. All right, this is a formula we have derived. This equation should be remembered, and we have shown that gain with feedback is independent of open loop amplifier gain, and that is equivalent to 1 by beta also. Okay, so this derivation, and we have solved one problem. Okay, there are so many problems are there, from the textbook Cedra Smith. Students should go through 6th edition of textbook and solve few problems, worked examples and exercise problems. If any doubts are there, you can bring it to my notice. We have covered even bandwidth extension also, and we modeled bandwidth, the entire frequency response, and especially for lower band we have an high frequency response, and that we have modeled as a single pole, and we said that its transfer function resembles this equation. Okay, so which is defined by equation 1, AFS equals AM divided by 1 plus S by omega h, where AM is the mid band gain and omega h is nothing but higher 3 dB cutoff frequency. And later we have shown the high frequency response through the S transform and little bit of mathematical manipulation. We have arrived at expression for transfer function, which you can see here, and from this we have extracted higher cutoff frequency expression WHF HF, you can see here. That is frequency, higher cutoff frequency is nothing but WH times which is 1 plus AM into beta. AM is nothing but which is open loop gain, and beta is the gain of the feedback network. And as you can see within the bracket, the higher cutoff frequency without feedback is multiplied with 1 plus AM into beta. This is the scaling factor. So when something is multiplied with already existing higher cutoff frequency, that means the overall with feedback the higher cutoff frequency keeps increasing. Since there is a scaling factor here, which is multiplied with omega h. Okay. On other side, you can see that lower cutoff frequency WLF, the scaling factor is in the denominator, as you can see here, 1 plus AM into beta. The same scaling factor is in the numerator with reference to higher cutoff frequency, whereas with reference to lower cutoff frequency, it is in the denominator. This shows that lower cutoff frequency decreases with feedback, higher cutoff frequency increases with feedback. Okay, suppose if this is going to be a frequency response curve, frequency response curve is nothing but it is V naught by Vi, it is a gain, this is a gain equation, and if we plot with reference to frequency, okay, so we can plot this as a curve for common source amplifier, it something goes to be like this. The mid band, there is a flat here, and the frequency decreases at lower frequency, and even it falls at higher frequency. Okay. And this you can decrease by 3 dB. Let me show with the dotted line here. Let us assume that this is going to be 3 dB drop, 3 dB decrease. This is as per the power transfer theorem, we need to decrease by 3 dB. Okay, so once you do that, you will have lower cutoff frequency FL, okay, and here we will have upper cutoff frequency FH. Okay, let us assume that this is going to be for feedback, so we can introduce subscripts here FLF and FHF. In our case, what happened is FHF has increased, FLF has decreased. We have shown in terms of omega. Okay, so there is no difference, just you have to divide by 2 pi for the frequency to obtain the frequency. Okay, so this shows that bandwidth has been extended. Okay, so because decrease in lower cutoff frequency, okay, so there is a drop and there is an increase in higher cutoff frequency, that means bandwidth keeps expanding. So bandwidth is nothing but difference between these two limits. So this is bandwidth, FHF minus FLF. The range of frequencies, okay, over which you can transfer signals is the bandwidth. Okay. So bandwidth has to be more, that is the advantage for us. So here we have shown only the high frequency response of an amplifier. Okay. So with and without feedback, as you can see here, the gain is plotted along y axis, the frequency omega is plotted along x axis. Okay, the blue color line, what you see here is the response, frequency response of an amplifier without feedback. A means it is a gain without feedback. So you can see that high frequency response is constant till we reach the cutoff frequency, say this is omega h, and there onwards you can see this is the cutoff frequency decreases, drops at the rate of 20 dB per decade. So this is minus 20 dB per decade. That means for every 10 times increase in the frequency at the scale of 10, gain drops by 20 dB. This has to be expressed in decibels. Okay. That means if you move from 10 to the power of 2, let us say this is 10 to the power of 2 to say 10 to the power of 3, 10 times there is a increase in the frequency. This is 100 and this 10 to the power of 3 is nothing but 1000, and the gain will drop by 20 dB for every 10 times increase in frequency. Okay, so gain drops by 20 dB, that is the meaning of this 20 dB per decade. This is also called as roll off rate, roll off, the rate at which the gain drops okay, is nothing but roll off at the rate of 20 dB per decade. It is a first order system, therefore, it is 20 dB per decade. For second order and subsequent orders, the roll off rate will be rapid. For second order, it is going to be 40 dB per decade, and for third order, it is going to be 60 dB per decade. So, that means order should be multiplied with n here. Okay. So, n is equal to 1 means it is 20 dB per decade, n is equal to 2, it is 40 dB per decade, that is second order system. Like that system, order wave filter, when it keeps increasing, the roll off rate also keeps increasing, but the transfer function becomes complicated when you go for higher order. So, we will see these type of things in while designing the filter. In upcoming modules, we will discuss about that. Okay, here what you want to make an observation is this is a response frequency response curve without any feedback, as you can see here, and this is mid band gain. Okay, AM is nothing but mid band gain. Okay, so gain mid band gain is constant up to omega h, and there onwards it the gain drops here. Okay, so next, once you apply the feedback, the gain is denoted as AF here. So, this is the mid band gain for AF. As per our derivation, mid band gain with feedback is given by AM divided by 1 plus AM into beta. As you can see that mid band gain decreased compared to without feedback. Without feedback, it is large here, and it has dropped by 1 plus AM into beta. The gain drops because the moment you apply the feedback, and simultaneously you can see that there is an increase in the frequency. Earlier the cutoff frequency was here without feedback. Now with feedback, the cutoff frequency has been increased by a factor of 1 plus AM into beta. Look at that, the scaling is 1 plus AM into beta here. For the gain, it is in denominator. So this shows that gain dropped with feedback, whereas higher cutoff frequency increased with feedback. So this is the frequency response curve for an feedback amplifier. Noise reduction, we will see next is noise reduction. Any questions about this frequency response of feedback amplifier? I hope everybody is following me. Any doubts are there, please clarify here. All these materials are taken from the Cedra Smith textbook. Students can refer to this 6th edition Cedra Smith textbook. So all this material, the notes is prepared from that textbook. Next important property is noise reduction. As we said that by applying negative feedback, noise is going to get reduced. Okay, noise is going to get reduced. We will see that how this noise reduces here. Negative feedback reduces the noise or interference in an amplifier. Often in an amplifier we will come across the noise, or it is also called as an interference at different places. When we say noise in an amplifier, it may be generated within the device. When I say device, it may be the BJT or MOSFET or FET. Any of these device may generate noise. Okay, so transistor noise, that is also called as a transistor noise. Or also noise may be introduced in the circuit also, because other elements like in an amplifier we use capacitors, resistors, AC source, DC source. Okay, so from various places noise may be generated. Okay, so now by applying negative feedback, the amount of noise get reduced by applying the negative feedback. Okay, and the once noise get reduced, there is an important performance metric called as signal to noise ratio. This term becomes familiar when you go for higher semester, when you study subjects related to communication system. You will pay an attention to this SNR. Shortly we call this as an SNR. SNR stands for signal to noise ratio. Okay, so signal by noise, the ratio of this is called as signal to noise ratio. From a communication system, what we expect is noise should be as small as possible, signal level should be as high as possible. So overall signal to noise ratio should be very high. Higher the signal to noise ratio, that means the communication system has got reduced noise. We can't eliminate noise, noise will be there always, we can't make it 0, but to some extent we can reduce the noise. So now we are discussing this noise reduction with reference to amplifier, not with reference to communication system. So let us see that how we can reduce noise in an amplifier by using a concept called as negative feedback. So, here we discussed about source of noise, where it is coming from, which are the places in an amplifier the noise comes, and we are giving even solution to that. Solution is just by employing negative feedback, noise becomes very less. Okay, and conversely you can see that the signal to noise ratio keeps increases when the noise quantity becomes very less. Okay, so the noise reduction process is possible only at certain conditions here. Okay, that means there are certain assumptions are there, only when we met that condition or that assumption, then only this noise reduction process is possible, otherwise it is not possible. We will take you to the block diagram where we are going to explain the situation, okay, how we can reduce the noise by employing additional blocks to the existing amplifier block, which is A1, which has got the input signal as Vs and output signal as V naught. So, this is the block diagram, as you can see here, this is the block diagram. Okay. So, we will see that how we can reduce noise in this block diagram, each and every block we will explain. Okay. So, here so that is the thing here. I hope you understand the prior conditions here. Only under certain conditions noise will can be reduced, and situation is nothing but we have an amplifier here with gain A1, input signals is source is Vs, labeled as Vs, and noise or interference is labeled as Vn. So, noise can be either voltage or current, but here we assume that noise is a voltage signal. So, that is why we indicate noise signal as Vn. This can be positive or negative, we do not know, because noise is random in nature. Okay. So, noise can be sometimes positive, sometimes it can be even negative also. Okay. So, this is the assumption what we do, and also it is assumed that for some reason that amplifier suffers from noise. I told you the source of noise where it has come from. It may be from active device such as BJT, or it may be from passive devices also. Let us assume that there is some noise in the amplifier circuit. Okay, for some reason the noise has already exist. Okay, that means amplifier is suffering from noise, and that noise can be assumed to be introduced at the input of an amplifier. Okay, so here the assumption is, I told you there are certain assumptions which we need to meet in order to show the possible solution to reduce the noise in an amplifier. So the noise is we assume that it is at the input of an amplifier. Okay, not at the noise is not introduced within the amplifier, it is at the input of an amplifier the noise has been introduced. This can be understood by looking into the diagram here. This is the diagram which we have picturized here, so that you can understand, this is an amplifier, basic amplifier. This is a basic amplifier. So, here we are not specific to either BJT or FET, it can be any type of amplifier. Generally any amplifier, let us assume that here at the input there is some noise or interference, that is labeled as Vn. Okay, you can see that we have shown that as a voltage source, along with your input signal that needs amplification, source signal Vs. Okay, so we have a noise or interference signal. Here we are not showing any resistances like internal resistance of AC source and other things to make the explanation or the concept easier. We are eliminating all those things. Only important elements we are going to show here, especially the AC signal here, and the noise that is introduced along with the AC source is labeled as Vn here, and this is a block diagram of a basic amplifier. Inside this you may see a BJT or FET in the form of common emitter for the BJT and common source for the MOSFET. And output signal, as you can see here, this output signal which is now amplified by A1. A1 is nothing but gain of the amplifier, and now input is not only Vs, but also it has got Vn, and we do not know the magnitude of this. Vn may be smaller, Vn may be bigger, but this still it gets adds with the source here, and so that overall quantity is very large now. Suppose if I take an example of Vs as say 100 millivolt, let us say, and Vn may be say 10 millivolt for example. Assume that this is going to be a small signal amplifier. So, total voltage now is nothing but 110 volts millivolts, and this gets scaled up by the amplifier gain, and now quantity becomes very large now, that is going to be the V naught here. Okay. So, now signal to noise ratio definition is Vs by Vn. If we take a ratio of signal component by the noise component here, so it is ratio of Vs by Vn, that is called a signal to noise ratio. Higher the signal to noise ratio, it is better, that means Vn should be less and Vs should be larger. Okay, now let us see, this is an illustrating application of negative feedback amplifier in order to improve the signal to noise ratio. And what is the difference between this block diagram we have discussed here and this one? Here it is nothing but we have shown where the noise has origin, noise has been origin, which is that we have introduced at the input of an amplifier, and there is an amplifier here, and the output you are seeing both source signal and noise signal which are amplified by A1 times here. The same amplifier, now we have to reduce this noise. In order to improve the signal to noise ratio, Vn should be less and Vs should be larger, and we have an alternate block diagram here which will illustrate how to reduce noise here. And let us understand each and every block of this diagram. A1 is nothing but which is a basic amplifier, and A2 is another amplifier which is a clean amplifier. Okay. So, this is A2 whose gain is labeled as A2 here. This is a clean amplifier. What do we mean by clean amplifier? The amplifier without any form of noise, that is a clean amplifier. This is an assumption here. The assumption what we do here is a basic amplifier A1 follows precedes the clean amplifier here. The clean amplifier means in an amplifier without any kind of noise, that is the meaning of clean amplifier. So, to reduce noise introduced by this kind of amplifier, when I precede this amplifier with noise with a clean amplifier, and so along with feedback, okay, the noise level is going to get reduced. We will show this mathematically also, and later on we will illustrate that through an example as well. Okay, I hope you understand this diagram. Okay, so there is I repeat once again, there is a basic amplifier which we have shown, already discussed about that, and there is a noise which is getting added here to the signal which is coming here. Okay, so here we have a source signal which you can call as Vs1 here, and this as this as Vs1 and this as Vs2 you can call here. Okay, so this is the output of this clean amplifier. So, this amplifier we assume that it is free from all sort of noise. So, there is no noise component which is getting added here. So, now when this noise with an amplifier precedes a clean amplifier along with the feedback, so this certainly improves here noise level here, and overall signal to noise ratio becomes very less. Okay. And other signals like we have a beta network which is the feedback gain which is indicated as beta network, and there is a feedback voltage which is labeled as Vf, and Vf is equivalent to beta times V naught, and there is a Vs which is a source voltage that is get added because this is Vs is going to be in series with this beta V naught, and that is applied to the clean amplifier. These are the block diagram. Again there is a loop you can see here, you can make out here. Okay. Now, let us go through the mathematical aspect of this once we understood various blocks, how they are interconnected here. When you look at the traditional feedback structure, there will be a load here which is not shown here. There is a load, and there is a source here, as you can see. Just I am comparing this with our original block diagram. And now instead of having one amplifier, we have two amplifiers whose gain is A1 and A2. One of them is clean amplifier, other one is going to be the amplifier with a noise, and there is a feedback network of course. The feedback network will sample the input signal which you can see here, and this is called shunt kind of sampling. There is different types of sampling, series and shunt. Okay, since output is going to be a voltage as you are seeing here, we are going to sample the output voltage by taking voltage at two different points here. The output voltage is sampled, and that is provided as an input to the feedback network. So, this is a sampled voltage here is V naught, and that gets multiplied with feedback network gain beta, and finally we have Vf is equal to beta times V naught. This feedback voltage which is equivalent to Vf, that gets added to this Vs, and that is given as input to the clean amplifier. I hope this block diagram is clear to all of you. Then with that we will move to the mathematical aspect of this block diagram. And now let us see here. In figure 1b, I am referring to the second block diagram here, figure 1b. We assume that it is possible to build another amplifier stage with gain A2. A2 is nothing but a clean amplifier that does not suffer from any noise problem. Okay, if you are able to build an amplifier with gain A2 which does not have any noise problem, and that can be preceded with amplifier with noise. That's original amplifier with having gain as A1, and that precedes a clean amplifier with gain as A2. Further, negative feedback is applied around the overall cascaded arrangement that you have seen in the block diagram, so as to keep overall gain as a constant. Now we will look into the mathematical derivations part. The output voltage of a noisy amplifier is given by this V naught is equal to V1 times Vs plus Vn. Okay, if you have any doubt, you can look into the block diagram. Okay, A1 is nothing but this first one here, V naught, this expression we have written is A1 times here the Vs which is written as Vs here, Vs plus Vn, that is a signal here, Vs plus Vn. Okay, and the signal to noise ratio is nothing but, we already defined this, source voltage by the noise voltage, that is the definition. Now here there are two sources are there. Now let us apply superposition theorem for that. Okay, I hope you are familiar with superposition theorem. Whenever we have multiple sources in a network or a circuit, with various elements, then it is required to apply superposition theorem. Okay, this comes only into the play, superposition theorem, when there are multiple sources. But what superposition theorem says that only one source has to be active at a time. Okay, then we are going to measure output voltage with one source acting at a time. So as you can see here, so now here with Vn acting, Vn is 0. When Vn is made 0, the output voltage is calculated as V01 equals Vs times A1 A2 divided by 1 plus A1 A2 into beta. This general feedback definitions we are using here. We know that gain with feedback is AF is equal to A divided by 1 plus A into beta. But now look at here, once you make Vn as 0, go back to the block diagram. Once this is going to be 0, and now you can see that this gain gets multiplied, A1 into A2, that is the overall gain. Okay, now A becomes A1 into A2, that is the open loop gain. A should be replaced with A1 into A2 because there are two amplifier blocks. So now V01 output voltage is source voltage times A1 A2 divided by 1 plus A1 into A2 into beta. Okay, when this is the condition here, when one of the source is made 0. In our case, first case, we have made Vn as 0. Okay. Now next second case, superposition theorem, according to superposition theorem, when Vn is active, but Vs is going to be 0 here. Okay, now let us see what is the output voltage V02. Now here when once you make Vs as 0, okay, now you can see the A2 amplifier does not exist, only we have a noise signal which gets multiplied with A1, this is a noise amplifier, divided by, and there is a product of A1 into A2 into beta. Okay. So this is the scaling factor here, Vn into A1 divided by 1 plus A1 into A2 into beta. So in this you can see that this is the output voltage with only Vs acting as 0. Let us go back to the diagram and illustrate here. Once we make Vs is equal to 0, what is the resulting network here? So once we make Vs as 0, this component is 0, but this exists now. Earlier we made Vn as 0, and so we have multiplied these two gains, and we applied a feedback gain expression and used that gains in that expression. But now once we make Vs as 0, we have called output as V02, because for V01 when Vn is 0 we called as V01, but when Vn is acting but Vs is 0 we are calling output as V02. So, for V02, as you can see here, Vs does not exist, V02 is nothing but output voltage is A1 times the Vn divided by the total gains 1 plus A1 times A2 into beta, because this is a feedback network here. So, since this signal does not exist, so this gets this signal, the feedback signal comes only, it gets applied to the A2 directly without the Vs here. Okay, that is the reason here you see in this second equation A1 times Vn divided by 1 plus the output voltage, the feedback voltage is nothing but, so A1 A2 times, okay, so that gets multiplied with the beta here. So, this is for Vs as 0. Now, according to superposition theorem, these two voltages for Vn 0 and Vs acting alone, Vs exists here, whereas here Vs is 0, but Vn exists. So, these two conditions, output voltages we have labeled as V01 and V02. So, these two gets added up and overall output voltage is V0 is equal to V01 plus V02. Now, let us use this derivation equations here. So, finally, we can substitute this equation here, this equation in this overall output voltage equation. So, V0 is equal to Vs into A1 A2 divided by 1 plus A1 A2 into beta plus Vn into A1 divided by 1 plus A1 A2 into beta. Okay. And signal to noise ratio, as you can see here, signal to noise ratio is nothing but it is Vs by Vn. So, signal component by the noise component, and now we can see it only gets multiplied with A2. Between Vs and Vn, as you can see in the block diagram, only A2 exists. You can see here between Vs and Vn only A2 exists here. Therefore, so the signal to noise ratio is now, as you can see here, it is Vs by Vn. As you can see here, signal to noise ratio now depends only on the clean amplifier here. Okay. And here the noise level can be, now this gets, this complete component A2 gets multiplied with Vs, the overall signal component becomes larger. Okay, this factor, numerator factor you can see here, this factor is going to be very large, having same noise value. So, therefore, signal to noise ratio increases. Okay. So, from equation 4, signal to noise ratio is A2 times higher than the original case. When you compare equation 2 and equation 4, where is equation 2? This is equation 4, Vs by Vn. Now, you can see Vs by Vn that gets multiplied with A2 here, that is an advantage here. The improvement in signal to noise ratio by application of feedback is possible only if one can proceed the noisy stage by a noise free stage. This is the condition. Okay. And this fortunately we can meet this situation in most of the practical amplifiers also, especially in power amplifiers which suffers from a problem called as power supply hum. This block diagram that we have shown can be used in that. Okay. So, this power supply hum is due to the result of large current that is flowing in the power amplifiers, and there we can reduce the noise by using the existing block diagram that we have shown, and also signal to noise ratio can be considerably improved, okay, using the block diagram that we have presented. Okay. Now, to understand this concept, we have a example here. Consider a signal to noise ratio improvement circuit having output noisy power amplifier stage with a gain 5. Okay. Noisy power amplifier stage, okay, his gain is 5 given here. A small signal amplifier as a pre-amplifier with a gain 1000, okay, and a feedback network with beta is 0.1. If Vs is 1 volt and Vn is 0.5 volt noise voltage, as I told you, Vn is nothing but some form of voltage, it may be positive or it may be negative. Here in this example it is positive, the noise voltage is positive, and it is asked in the problem to calculate the signal to noise ratio voltages at the output and improve signal to noise ratio also. Also calculate total output voltage. This is very straightforward problem. If you understood the previous theory of noise reduction, definitely we can solve this problem. Now write down all the given data. A1 is pre-amplifier, which is given, gain is given as 1000. A2 with noise it is given as 5. Source voltage is 1 volt, noise voltage is 0.5, beta is 0.1. So all the given data has been written here. As you can see here, this is a block diagram we have designed for this problem. As you can see here, Vs, A2, A1, beta, Vn and V0. Okay, now we can find V01 and V02 by applying superposition theorem. So V01 can straight away use already derived equations, Vs into A1 A2 divided by 1 plus A1 into A2 into beta. So substituting all these values of A1, A2, beta and Vs gives the value of V01 as 9.98 volts. Okay, so this is due to the signal output voltage. So let us say for the noise output voltage V02, okay, the formula is Vn times A1 divided by 1 plus A1 A2 into beta. See, these formulas what I am using here, students, if you find it difficult, write down at the end of the notes all these equations and memorize them, so that in this chapter problems are very easier if you remember this formula. And slight mistake here, see, in place of A1 if you include A2, you are going to end up with a wrong answer. Be careful about formula also. You keep memorizing all these equations, it becomes easy for you. So substitute here for the noise voltage A1, A2 and beta. You are going to get output voltage due to the noise, as you can see here, is very less voltage, which is 0.00998 volt. Now let us measure the signal to noise ratio at the output, which is V01 by V02, 9.98 by 0.00998, which is 1000. This also can be expressed in decibels by using 20 log 10 of 1000, which is going to be 60 dB. And next we can calculate total output voltage, which is 9.9899 volts. That is the total output voltage of this amplifier circuit. Any question about noise reduction property? So far we have discussed this noise reduction property. I hope we have solved even example to understand the concepts what we have discussed. And next we are moving to the another important property of feedback, negative feedback amplifier is reduction in non-linear distortion. Are there any questions to answer at this point? Any doubts or questions are there from students? I hope everybody is with me. Reason is these properties are important, as I mentioned in the last class itself. At least know the 3 to 4 properties they may ask you in examination. Be familiar with all mathematical formulas, and even sometimes they may ask even problems also. Okay. Be prepared for both theory and problems, okay, about on this topic. Okay, if you do not have doubts, let me move on to the next important property, which is non-linear distortion. So far we have seen the noise component which is present in the amplifier, and we have shown the solution to reduce the noise in an amplifier with a new block diagram that we have presented. Another problem in any amplifier circuit is basically non-linear distortion. Many times see this kind of distortions we will see when we rig up an amplifier in the laboratory and observe the output waveform, but these distortions we ignore it. Sometimes distortions may or may not be visible also, okay. But again, when we say even it is visible also, you should see the source of this distortion, where the distortion has come from, okay, whether it is from the active device or from any other device, we have to see that. Basically the active device BJT or FET, okay, that is a non-linear in nature. That means between the input and output, the BJT or FET does not exhibit characteristics like this, 45-degree line like this, okay. If any device exhibits this kind of characteristics 45 degree from the origin, that is a linear. See, we already seen the transfer characteristics of BJT or FET. It is something like this, right? It is something like this. When we plot an output and an input. Now look at here, this is non-linear. We expect active devices to perform like this, to behave like this, but they are non-linear in nature. Somewhere they are going to be linear, as you can see here. Small piece of this is called piecewise. We can approximate it as linear. In case of, since the device is non-linear in nature, it results in no distortions also. When we try to use amplifier in non-linear region, it results in a distortion. In case of non-linear distortion, additional frequency components at multiples of fundamental frequency are present in the output. I hope you are understanding this thing. When you observe signal component at the output of an amplifier, I mean the sine waves here like this. The fundamental frequency will have, because every signal will have its own fundamental frequency also, and you will see the harmonics like this, which is appearing in the same line, the second harmonic, third harmonic like this. They are not cycles here, it is harmonics I am saying here. Okay. And these harmonics are not essential, but only the fundamental frequency is essential for us. This second harmonic, third harmonic, you may have fourth, fifth like that. Those harmonics are nothing but they are the distortion. And here we use a term called as harmonic distortions. Okay. Probably you might have seen harmonic series in your mathematics, right? Okay. Geometric series, arithmetic progression, geometric progression, harmonic progression. Similarly, here we have a distortion here as harmonic distortion. Harmonic means it is the distortion whose frequency is multiple of fundamental frequency. Fundamental frequency, if it is going to be say f naught, and the distortions may have frequency like 2 times f naught, 5 times f naught, like that. They are the multiples of this fundamental frequency, and such distortions has to be eliminated, otherwise it creates a lot of problem and consume power in communication devices as well. And here we have a plot here that illustrates usage of negative feedback in order to reduce the negative or non-linear distortion in an amplifier. Look at this amplifier, the negative feedback reduces non-linear distortion. When we design an amplifier, you will get to know, okay, when you can make an observation without feedback, how this non-linear distortion is going to create a problem, and with the feedback we can bring down this non-linear distortion. Non-linear means, as I already told you, it is a second, third, fourth harmonics in the waveform. Okay. We have shown even this harmonic distortion in the while deriving the expression for voltage gain in BJT based amplifier and even FET based amplifier also. And this non-linear distortion can be easily brought down, because the distortion term you can see here is present in denominator, therefore D non-linear distortion will be reduced by a factor of 1 plus A into beta. This much amount of time the non-linear distortion can be reduced by employing a negative feedback. That is the concept or idea here. Okay, let us see here the graph of V naught versus Vi. Okay, you can see this is total graph is basically non-linear, but we can see this as a piecewise linear. So you can see, observe here, from here to here it is linear, and it follows another linearity from here to here, and then onwards it becomes a flat. Okay, you can see, you can write any curve, a non-linear curve, in a piecewise linear also. Entire curve is non-linear, but small pieces are linear. That is the meaning of piecewise linear. Okay. Between 1000 to 100 voltage gain, that is going to be linear. As you can see here, this gain is 1 by 0.02, V naught by this 0.02. Gain is V naught by Vi. V naught by Vi. In this case, suppose if I want to calculate gain here, this first one red color indicates a graph, a response, okay, transfer characteristics, because this is a graph of V naught versus Vi. This is not a response, it is a transfer characteristics. So, the transfer characteristics for an active device without feedback is shown in red color, as you can see here, and with feedback, as you can see here, with 0.01 or 1% feedback when we provide, then you can see the transfer characteristics, okay, which is the blue color line what you are seeing here. Let me show that. This is a blue color line. This curve is a transfer characteristics for feedback amplifier. The other one is without feedback, as you can see, which is shown in the red color like this. So, we have drawn this like a piecewise linear, because entire device is non-linear in nature. Okay, any questions about this frequency response? Frequency, so the transfer characteristics. So, this is the transfer characteristics of an amplifier with and without the feedback what we have shown here. Figure A shows transfer characteristics of an amplifier. The characteristics is piecewise linear with voltage gain changing from 1000 to 100 and then to 0, as you can see here. So, as I told you how to calculate voltage gain, just divide this voltage V naught by V in Vi, that gives you the voltage gain 1 by 0.02, 2 by 0.04, like that, and this value can draw a straight line here, and approximately you can draw, I can show you vertically, you can draw downwards, and it may be 0.03 this value. Now you can calculate what is voltage gain, 4 by 0.03. Okay, that is how we can calculate the transfer characteristics gain value. Okay, so transfer characteristics can be considerably linearized, by which you can make it as a linear using negative feedback. We know that feedback reduces with the feedback reduces AF by an amount of 1 plus beta, and if I assume that AB is greater than 1, 1 can be neglected here. AB is far greater than 1, 1 becomes less, and if in the gain expression if 1 is eliminated, so the AF becomes now depends on only on the beta. Okay. So, large change in the open loop gain give rise to a smaller change corresponding to the closed loop gain. This AB is nothing but it is a open loop gain, which if I assume it is a large, then the total amplifier gain with the feedback reduces, it becomes independent of the open loop amplifier gain. And here we have a problem which you can which illustrates that concept. Beta is 0.01, A is 1000, and you can calculate AF value, okay, by using A divided by 1 plus A into beta. This is A, this is beta, and this is A. A is 1000, beta is 0.01. This value gives us 90.9. Use this equation to arrive at AF1. So, here you can see 1000 amplifier gain is 1000, and if the gain is 100 basic amplifier gain, and now you can see that AF2 gain with feedback is now increased or decreased compared to this value. So, you can see 90.9 as reduced to 50 here. Okay, but you can see the gain, basic amplifier gain has been reduced from 1000 to 100 here. There is a 10 times which is a drop here, but look at here the gain is also reduced by twice, approximately twice. Okay. The order of magnitude change in slope has been considerably reduced. The price paid is reduction in the voltage gain. If the overall gain has to be restored, then a pre-amplifier should be added. That is what the conclusion from this. Okay, so there is another problem which you can see here. An amplifier has a mid-band gain of 125 and a bandwidth of 250 kilohertz. If 4% negative feedback is introduced, find the net new bandwidth and gain. If the bandwidth is to be restricted to 1 megahertz, find the feedback ratio. This is a problem related to the bandwidth. Okay, so just a straightforward problem again here. you can solve it by substituting this AV, bandwidth and beta. You can calculate gain with feedback, then you can calculate bandwidth with feedback, which is going to be 1.5 megahertz. This is with feedback, and look at without feedback, it is going to be 250 kilohertz here. And again you can see the second one is if the bandwidth is restricted to 1 megahertz, what is the feedback network gain. So this can be calculated by using same equation. Bandwidth bandwidth with feedback is equal to bandwidth into 1 plus AV into beta. Substitute all the values which we know. So here we need to calculate the beta with the gain as 125. Okay, so you can see here this is a bandwidth without feedback is given as 250 kilohertz, and finally we got to know the value is beta is 0.024. So in order to have a 1 megahertz bandwidth limit, we need to have a gain beta feedback network gain as 0.024 here. I think we will stop here at this point of time. We have covered almost all properties of a negative feedback amplifier. If there are any questions which you can take up. In the next class, we are going to start with the 4 basic feedback topologies. Okay, it is an important again from examination point of view. So we will cover the important topologies like voltage amplifier, current amplifier, transconductance and transresistance amplifier, with all the relevant derivations like gain, input and output impedances. Oh, okay, we will stop at this point. Later on, we will continue in the next class.